Measuring blood flow. Blood contains positive and negative ions and thus is a conductor. A blood vessel therefore can be viewed as an electrical wire. We can even picture the flowing blood as a series of parallel conducting slabs whose thickness is the diameter d of the vessel moving with speed v. So you can see that we have this diameter is d, it's moving with speed v, so it's like a conductor. Part A. If the blood vessel is placed in a magnetic field B, perpendicular to the vessel as in the figure, so this is into the page, show that the motional potential difference induced across it is BVD, the product of the magnetic field magnitude, its speed, and its diameter. Now, if we place this blood vessel in a magnetic field and it enters this magnetic field, it's moving in this magnetic field, in a time interval t, let's say that this is the beginning of the vessel, the total amount of the vessel, the total length inside the magnetic field will be Vt. Now you can see that the positive charges will feel the Lorentz force. So what is the Lorentz force? QV cross B. V cross B, if I have my four fingers of the right hand pointing in the direction of the velocity and curl them towards the magnetic field, the thumb points upward. So that implies that positive charges will start accumulating on this side and negative charges will start accumulating on this side. Now, what is the magnetic flux that is developing in this region? The magnetic flux is the product of the magnetic field with the area. So it's B times Vt, the length inside the magnetic field, times the diameter d. So you can see that this rectangular region is basically the perpendicular area for the magnetic field, and that's the flux. So if I write d phi b dt, the rate of change of flux, d phi b dt, it is b v d. So basically the time derivative will get rid of this t, and since the magnitude of the EMF is going to be equal to d phi b dt, this is the absolute value of the EMF, so we can see that the EMF that will develop here is BVD, and it's going to be such that positive charges will start accumulating on top and negative charges at the bottom, as you can see in this figure, and this is called motional electromotive force, EMF. So it's due to the Lorentz force felt by positive and negatively charged ions moving inside this vessel. Let's move on to part B. If you expect that the blood will be flowing at 15 centimeters per second for a vessel 5 millimeter in diameter, what strength of magnetic field will you need to produce a potential difference of 1 millivolts? Well, this is direct application of the calculation we did in part A. The EMF that will develop here is BVD. Now, that means the magnetic field magnitude B you would need for a given EMF we're targeting is epsilon divided by Vd. And we want to have 1 millivolt EMF induced, 1 times 10 to minus 3 volt. velocity is 15 centimeters per second, 15 times 10 to minus 2 meters per second for a 5 millimeter diameter, 5 times 10 to minus 3 meters. This is 100 divided by 75. So the magnetic field we need is then 1.3 Tesla. Okay, so in order to induce this EMF on this vessel. So let's move on to part C. Show that the volume rate of flow, capital R, of the blood is equal to capital R equals pi epsilon d divided by 4b. Note, although the method developed here is useful in measuring the rate of blood flow in a vessel, it is limited to use in surgery because measurement of the potential epsilon must be made directly across the vessel. So volume flow rate of the blood can be measured with this technique in a surgery. Okay. So what is the volume that is exposed to magnetic field B that is pointing into the page? This volume, as we have shown here, is the area of one side, one cap, which is pi r squared, multiplied by the length, which is Vt. So the volume exposed to the magnetic field is pi. The radius is diameter divided by 2. So pi r squared is pi d over 2 parentheses squared, and Vt. So in a time interval t, starting at t is equal to 0, we enter the magnetic field. We have this volume. Now, what is dV dt? Rate of volume flow. It is pi d squared over 4 times v, its speed. But at the same time, we know that its speed v is the motional EMF induced epsilon divided by the magnetic field times the diameter of the vessel. Therefore, the volume flow rate, capital R, becomes pi d squared over 4 times the speed, which is epsilon divided by BD. So therefore, we find that the volume flow rate is equal to the measured induced EMF pi times the diameter of the vessel divided by 4 times the magnetic field, applied magnetic field magnitude. So as suggested, this is a method to measure the rate of blood flow in a vessel, but only in a surgery because EMF has to be measured directly. So here we have seen an example of motional EMF. For the blood vessel here, we can think of positive and negative ions that are basically moving with velocity v inside this cylindrical conductor. And when it enters a region with magnetic field B, according to Lorentz force Q V cross B, right hand forefingers pointing in the direction of velocity curling into the page, the thumb points upward, a motional EMF will be induced. If the region inside the magnetic field, so we start our timer at t is equal to 0 and we wait for a time t, Vt is the length of the blood vessel that is inside the magnetic field. Then we can see that the magnetic flux is BVT times d. So Vt times d, the diameter, is the area that is exposed to this magnetic field, and this is the flux. d phi b dt is the motional EMF, BVD. And we can give it some numbers. That's what we did in part B. For a 5 millimeter diameter vessel and 1 millivolt EMF we want to measure with a blood flow rate of 15 times 10 to minus 2 meters per second, we need 1.3 Tesla magnetic field. The volume flow rate is basically the volume that is inside this magnetic field, which is pi r squared multiplied by the length, pi d over 2 parentheses squared vt. That's the volume. dv dt, rate of change of volume in time, is pi d squared over 4v. Because v is epsilon over bd, we can write the rate of volume flow this way, as suggested in part C of the problem.